Hi everyone and welcome back to PrepFusion. I am Anish and today we will start with the lecture 3A of our two-port networks, that is H and G parameters. Also we will discuss about ABCD parameters. So what are H parameters? So H parameters are referred to as hybrid parameters. Why are they called hybrid parameters? Because I can write my voltage in terms of current and voltage. So I write my input voltage in terms of input current and output voltage, and I write my output current in terms of input current and output voltage. So it's like a mix and match, right? So that's why it's a hybrid of voltage and current. So that's why the name hybrid parameters. Okay, so in some cases Z parameters, Y parameters may not exist for certain networks like a transformer. So in those cases we can use hybrid parameters. Okay, so in hybrid parameters, just one thing you have to keep in mind is what are my independent and dependent variables. So what are my independent variables? My independent variables are I1 and V2, basically the input current and output voltage. So from here, right, from here one onwards, remembering the formulas is bit difficult, like H11, H22. So what you have to remember? You have to remember this thing. If you remember this thing, right, then you will be able to remember what is my H11, what is my H12, because I know where will the problem be. The problem will be in remembering what is H11, what is H12, what is H21, what is H22, because there will be a confusion. Because previously you know what is Y. Y is the just ratio of current and voltage. So it was very simple and easy. But here, right, it will not be that simple and easy. So just be careful regarding that. Okay. So what about here? And what is the dependent? What are the dependent variable? I will tell you how to remember. I will tell you what are the dependent variables. Dependent variables equals to my I2 and V1 basically. So this thing you have to remember. If you remember this, then you will be able to remember the formula. So if this is the equation format and this is the matrix format. Okay. So like these are the descriptions of H11, H212, H21, H22. So if I have to find out H11, what do I need to do? So I need to first make V2 0, then the ratio of V1 by I1 will give me H11, as it is a ratio of voltage and current. So that's why unit is ohms, and it is called short circuit input impedance. Why is it called short circuit input impedance? Because I make my voltage 0. That's why it is called short circuit input impedance. And what about the H12? H12, right? What do I have to do? I have to make I1 0. I1 0 means open circuit. Open circuit the input terminals. If I open circuit, then the ratio of V1 over V2 will give me H12. Okay. So if I open circuit, like it will be basically unitless. Okay. It will be basically unitless, and this is H12 basically. And I2, what is I2? I2 is equals to H21 I1 plus H22 V2. So again, if you make V2 0, your H21 will be I2 upon I1 and H22 will be I2 upon V2. So how do you remember this thing, right? How do you remember this thing? My suggestion would be, no need to remember this. Okay, whenever you are solving any each parameter question, you write down the equations. So what I have told you to remember, what have I told you to remember? I have told you to remember what are my independent and dependent variables. What are my independent variables? My current, input current, port 1 current and port 2 voltage. Good. So first, right, first thing in your mind should come is automatically we always write V1 at the start, right? For Z parameters we used to write V1 at the start. So I will write here V1. So once I have written V1, so of course V1 cannot be here, right? V1 cannot be here. So I remember in hybrid parameters there is a current and voltage. So voltage V1 has been used, so another voltage will be V2. So V2 will be here, and it will be in the second column. Why? Because the subscript is 2. That's why it will be in the second column. As the subscript is 2, that's why it will be in the second column. Then in the first column, what will be the voltage? In the first column, the voltage, the current will be I1. In the first column, the current will be I1. Okay. In the first column, the current will be I1. Because of course there has to be one current, right? And I have already taken V2, so I cannot take I2 here, because here whatever component I will take, its subscript should be 1, right? It cannot be 2 because I am taking in the column 1, first column. So it has been I1. So now it is fixed, right? Now it is fixed. Now it is very simple. Now you just write here H11 plus H12. Okay, plus H12. Now what is my like what is the other variable? I have taken V1, I have taken I1, I have taken V2. So what is left? I2 is left. So ultimately I will write here I2. I2 will be equals to, now it is simple, right? I know my independent variables I1 and V2, so I will write here I1 and V2, and like what is left? This is H21 and plus H22. So you don't remember them individually, you just try to write down the equation. That is your main task. Try to write down the equation. Okay, so please rewind this again, rewatch this again. If you are not like not able to understand it, rewatch it again. So this is the way that you should remember this thing. Okay, so this is the best way. Basically, individually if you try to remember, you will mess up, you will do some mess up. Okay, try to write down the equation, and from there you, I hope from here you can ultimately write what is H11. H11 is V1 upon I1 when my V2 is 0. So yeah, I hope you understood this point. So like these are the names, basically not that important. Why open circuit reverse voltage gain? Because it is a ratio of voltage, and reverse voltage gain because I am taking V1 upon V2. Okay, and it is a ratio of open circuit voltage because the current I2 is, sorry, the current I1 is 0. That's why it is open circuit. Here again it is short circuit forward current gain because the ratio of currents, and short circuit because the voltage is 0. And here H22 is the open circuit admittance because it is the ratio of I2 by V2. And of course the current is 0, that's why it is open circuit. Okay, so these things are very simple, not that difficult to understand. So practically how do you measure this, right? Practically how do you measure this? So practically like in labs or something, how will you find out the H11 H22 parameters? So practically what you will do is you will like let's find out H11 and H21. So to find out H11 and H21 we have to make V2 0. So basically V2 will be shorted. V2 will be shorted. Okay, so if V2 is shorted, now I will have a voltmeter that measures the voltage across the port 1. So we'll have a voltmeter here. Okay, and I will have a ammeter in the port 1, right, that measures the current. So I will have a ammeter here, and I will have a what do you say, I will have a ammeter in the port 2 because I need to measure I2 as well to find out H21. So I need to have a ammeter here. Okay, so basically, right, what is my H11? H11 is V1 upon I1 when my V2 is 0, and H21 equals to I2 upon I1. Okay, where my V2 is again 0, right? So that's why I need a ammeter in the output, I need a ammeter in the input, I need a voltage source in the input. Okay, so these are the things basically. So now what I can say is now what about the other portion, right? What about the H12 and H22? So for H12 and H22, right, we have to open circuit the input current, right? We have to make I1 0. So if I make I1 0, I will connect a voltmeter. Voltmeter will be here. Voltmeter, will it be here? So what are my equations? These are my equations. So I know I don't need a voltmeter. I don't need to measure current. I don't need to. Okay. If I make I1 0, yeah, I will need a voltmeter. I will need a voltmeter, right, to measure V1. So I will need a voltmeter here. Also, I will need a voltmeter here. Okay. Also, I will need a ammeter here. Okay. So why do I need an ammeter here? I need an ammeter here because to measure this I2 current. So what is my H? What is my H12? H12 is V1 divided by I2. That is I1 when my I1 is 0, and H22 is I2 divided by V2. When my I1 is 0 again. Okay, so these are my H parameters basically. So yeah, that was about it for the H parameters. That's how you measure the H parameters practically. I'm talking about practically. So again, your H parameters will not exist. So like this is what is written over here. How do you measure? And this is the model basically. Not that important. You can understand about the model. Okay. So keep this in mind that like the model I can explain a bit. So basically, the input side of the model has a what? This is a voltage controlled voltage source, and this is a current control current source. Why is that the case? If I see the first equation, right, if I copy this equation, if I see the equation has a has its own current, of course, is there, and has a dependence on the output voltage. So we are writing voltage, so ultimately that's why it is a voltage source that will get added, and this volt, like it is dependent from the voltage of the port 2. So that's why it is a voltage control voltage source. And on the other side I have a current source. So on the other equation, on the second equation, I have a current. So that's why there is a current source here, which is a combination of this H22 and this H21 into I1, because it is also a current. So that's why it is a current control current source. So these are the two equivalents of the model. Of course, this is not a unique mapping. There can be many more models. Okay. And one more thing is that same thing whatever we have been learning is that my if my I1, like my I1 and V2 are independent variables, right? If my I1 is only function of V2, or if my V2 is only a function of I1, then I can definitely say, then I can say my H parameters or hybrid parameters does not exist, does not exist. Okay. So yeah, this is one thing you have to keep in mind. And generally, right, if you have studied BJT, you will know that BJT is modeled using H parameters. Okay, so we model BJT using H parameters. That point will come later on. So yeah, that was one more point. And inverse hybrid parameters is just the inverse, right? It is similar to it is similar as Y parameters is to Z parameters. So Y is the inverse of the Z parameters, same G is the inverse of the H parameters, and generally we don't use it. We mainly use H parameters only, but obviously I have to teach, so I will teach you everything. So H parameter is just the opposite. So here, right, my it will be just inverse, right? So here my independent variables independent variables will be what independent variables will be the opposite. So it will be I2 and V1. If you see, it is I2 and V1. Independent variables are opposite, and my dependent variables are opposite. Dependent variables are basically my V2 and I1. Okay, so like how to remember? No need to remember. So I will say here key point that just remember, just remember just remember H parameters and G parameters and G parameters will be opposite. Okay, so that is what you have to remember basically. Yeah, that is the one thing that I wanted to discuss here. Now, like these are a few key points that hybrid parameters are widely used in transistor modeling, mainly in BJTs. So we generally use hybrid parameters in BJTs. If you have studied BJTs, you will understand. They are easier to measure experimentally, okay, than other parameters. It is bit easier to measure, right? Measurement is easier for this type of parameters. And yeah, G parameters are used for modeling field effect transistors, which are not required, okay, which are not required to understand. So basically, right, how can you write convert from H to G or G to H? So your H parameters is here, okay, that is H11, H12, H21, H22. And again, for G parameter to exist, okay, another key point here, G parameter does not exist if G parameter does not exist if my so what are the independent variables? I2 and V1, I guess. Yeah, I2 and V1. So if my I2 is a function of only V1, or my V1 is a function of only I2, okay, so that is what you have to take care. And like my G parameter is this, right? G is some G11, G12, G21, G22, okay. So from here I can directly say that my like basically inverse G will be the inverse of H, or H will be the inverse of G, okay. So basic simple inverse, right? So simple inverse, if I do, G parameter will be equals to the delta H, 1 by delta H, determinant of the matrix, then of course the main diagonal elements will be swapped. So I hope you know how to find out the inverse of a matrix. If you don't know, what can I comment? Like you should know, right? I think in 11th only we study how to find the inverse of a matrix. So this will be H22, like the main diagonal elements will be swapped. So this is a shortcut for inverse of a 2 cross 2 matrix, and the off diagonal elements signs will be changed of the off diagonal elements, H11, H21. And here as well same thing will happen. Here my H parameter will be equals to 1 by delta H, this will be G22, G12 minus G21, G11. Okay, so yeah, this is H parameter and that is G parameter. This is how you find it, and like whatever I mentioned, like the same thing, how will they exist, if they do, if they exist or not exist. Okay, so that is what I have written over here. Now this you have to unfortunately memorize. This one you have to memorize. I very rarely say few things to memorize. This one you have to memorize. The condition for symmetricity and uh, reciprocity. So this, right, you have to remember in the memory, in the memory. So the condition for reciprocity is very similar to z and y parameters. For z parameter it was z12 equals to z21. For y parameter it was y12 equals to y21. For h parameter the difference is it is also h12 equals to h21, just a extra negative sign will be there. Now how do you remember this? So just remember, try to remember this. Okay, I remember z parameter has z12 equals to z21, y parameter has y12 equals to y21. I remember it is almost similar, each parameter condition is also almost similar like z and y, just a extra negative sign is there. So just a small variation is there. So you will write here h12 equals to h1 and then you will remember, okay, there is a small variation, that is a negative sign. Okay, so that's how you remember for the h parameter. Got it? And what is the symmetry condition? Symmetry condition is, again, unfortunately this one is quite a lot different. So symmetry condition for y and z parameter, it was z11 equals to z22. For y parameter it was y11 equals to y22. But for h parameter it is that h or g parameter is determinant of h equals to 1, and for g parameter it is determinant of h equals to 1. And here, right, for g parameter also condition for reciprocity is g12 equals to minus g21. So how do we remember this one? So you already know that z was the inverse of y. So the conditions for reciprocity and symmetricity, if you observe, remains similar, right? So here also the condition for reciprocity and symmetricity will be similar only. This will not vary. And there is another parameter known as ABCD parameter. There, right, these things will be opposite. So there the reciprocity condition will be the determinant of the ABCD matrix will be 1. Okay, that is the condition for reciprocity in ABCD parameter that we will learn later on. Okay, so yeah, this is the first question. So we have to determine the h parameters. So let's solve. How I will solve. So first thing is, I always forget the h parameter. What are h parameters? So again I will think, okay, there was v1, so I will first write v1 here. I have written v1, and then I will remember, okay, v1 is already getting used, so I cannot use v1 here, so I have to use v2, right? It should be in the second column, so I will use v2 here. And if I have used v2 and I remember that it is a mixture of current and voltage, so it will, here obviously one thing is left, that is i1. Only I can place in the first column, I can only place i1. So now I will write the all the other things, that is h11 plus h12, and here it will be like what is left. So I have taken v1, i1, v2, i2 is left. So I will write here i2 equals to h21 i1 plus h22 v2. Okay, so ultimate thing is, I understand it will take you, it will cost you an extra 10 seconds, but at least there will not be any confusion and you will not forget the parameters, right? Because it is very easy to get confused, because there are total six parameters, although only out of 6, 4 are important: z, y, h and abcd. But like in the 4 parameters as well you can get confused. So that's why I am telling you, just try to write the equation by yourself, and that's how you will be in practice. So now we have to find out the h parameters. So we can do few experiments. Either we can write this directly or solve individually. So let's write things directly here. Okay, let's write things directly. So if I write things directly, I observe that if I copy this here, right, I observe that this is my v1, i1, i2, v2. So if I apply a KCL here and here, so if I apply KCL in the first position, so it will be v1 divided by 4 minus i1 plus V1 minus V2 divided by 6 equal to 0. So this will be V1 divided by 4 plus 1 by 6 minus V2 divided by 6 equals to I1. So my I can directly say this will be I1 I1 will be equals to like some value. So this is V1 into 10 divided by 24, so it is 5 divided by 12 minus V2 divided by 6. Okay, so these are the values basically. So now now like what I can do is I can so okay, I was in some other mind. So now I can write this second KCL, right? Second KCL. So second KCL will be V2 divided by 10 plus V2 minus V1 divided by 6 minus I2 equal to 0. So my I2 current is minus V1 divided by 6 plus V2 divided by this will be again this is V2 by 6, right? So this will be 10 16 divided by 60, 16 divided by 60. So I2 equals to minus V1 divided by 6 plus V2 if I multiply by 4, 4 by 15. So this will be 4 by 15. Okay, so but ultimately, right, I need V1 in terms of I1 and V2. So in this equation, I have V2, I have I1. Okay, I have V1 as well. So this is fine. This equation is fine. So I can get to this equation, right? So here I need to write V1 in terms of I1 and V2. So V1 from this equation, this is equation 1. So from this equation, if I convert my V1 is equals to, I will multiply by 12 divide by 5. So this will be 12 by 5 I1, and if I multiply by 12 this will be this will be plus 2 divide by 5. So this will be 2 by 5 V2. Okay, so this is the first equation. This is the first equation. What about the next equation? What about this equation I2 in terms of I1 and V2? So here I have I2, but here, right, I don't have I1 and V2, I have V1. I don't like this V1, I have to remove this V1. So how will I remove this V1? From here, use this equation. So this is the equation 2. So I2 is there already, V1 I will replace with this equation. By 6 is there, it is 12 by 5 I1 plus 2 by 5 V2. Okay, then plus V2 into 4 by 15 is obviously there. So this will be I2, this will be minus 2 by 5 minus 2 by 5 I1 minus 1 by 15 V2 plus V2 4 by 15. So I2 equals to, I2 will be equals to, this is minus 3 by 15, so sorry, plus 3 by 15, so this will be 1 by 5 plus 1 by 5, 1 by 5 V2. Okay, this will be plus 1 by 5 V2. So now it is simple, right? Now you can definitely write the each parameter. So each parameter will be this 12 by 5, that is 2.4 ohms. This will be 2 by 5, this will be ratioless, right? This will be 0.4 unitless, not ratioless, sorry, unitless. This will be minus 2 by 5, no unit, so minus 0.4, and this will be 1 by 5. 1 by 5 is 0.2 ohm inverse or Siemens. So it's better to write it like this. S, you can get confused with S. So like, what do you notice? I notice my H12 is equals to minus H21. So of course this was the condition for reciprocity, and of course we have already proved to you these, like, simple resistive network is always reciprocal no matter what. So which is true as well, right? It is reciprocal. So yeah, is my determinant equals to 1. So let me check delta of H. So if I check delta of H, right, it is 0.2. This will be 0.48 minus plus 0.16. So this will be 45464. So this will be 0.64. Okay, so again it is like not equals to 1. So of course it is not symmetrical, and of course we can see, right, because here I have 4 ohm, here I have 10 ohm, it will not be symmetrical. Homework for you is you change this angle, sorry, not angle, sorry, you change this resistance value. Okay, you change this resistance value to 4 ohms, and now you check the condition for symmetricity. You will see that your determinant of H is equals to 1 for this new modified network. Okay, that is the homework. Please do it by yourself, and if you don't do, right, it will be just like, what can I say, like, if you are like basically skipping these things, that means you are not obedient enough, and if you are not obedient enough, at the end it will cost you. You will not get the good rank. Okay, so just listen to me what I am saying. So try it out by yourself, modify this circuit, and then check for the condition if determinant of H is equals to 1 or not. So of course you can solve this individually as well. So we will try to solve this individually as well. So this was the method 1, where I directly used KCL. So what if I would have solved this individually? So if I would have solved this individually, so method 2 is solving it individually. Okay, so it will be basically, so first, right, again I will write down the equations. So already I have written the equations, so I will copy it. Whenever you are confused, right, what is H11, H12, always try to write down the equations. So first I will try to find out H11 and H21. So I will make V2 0. So I will make V2 0. So V2 is 0. So basically it will be short circuit. So this is my V2, this is my I2, this is my I1, this is my V1. Okay, so if I make V2 0, that means I am talking about H11, that is V1 by I1 at V2 equal to 0, and then I am talking about H21, that is my I2 by I1 when my V2 is 0. Okay, so V1 by I1 when my V2 is 0. So V1 by I1. So V1 by I1. So it is basically the input impedance seen from this, right? Seen from this port. So basically this is short circuited. So this 10 ohm is of no use. Basically this 6 ohm and 4 ohm are in parallel. So H11 is basically 4 parallel of 6 ohms. So it is 4 into 6 divided by 10. So it will be 2.4 ohms. H21 is basically the current ratio, right? I2. So I2 upon I1. So I have a current here, that is getting divided in this 4 ohm and in this 6 ohm, because this 10 ohm is irrelevant because the voltage drop across it is 0. Okay, so basically I can do current division, right? So this will be the current division, that is I1 I1 double dash, and let me name this as I1 dash. So I1 double dash will be equals to I1 double dash will be equals to the opposite resistance into the sum divided by the sum, right? I1 into 4 divided by 4 plus 6, current division rule. So this will be 0.4 into I1. Now keep this in mind that your I2 is not exactly equals to I1 double dash. Your I2 is the negative of I1 double dash. Okay, I2 is the negative of I1 double dash, so it will be minus 0.4 I1. I2 is minus 0.4 I1. So this is my I2 and this is my H11. So like what is the ratio? Basically I need to find out the ratio between I2 by I1. So I2 by I1 is my H21, that is equals to minus 0.4. Okay, this is what my I2 by I1 is equals to. So yeah, that's pretty straightforward and pretty simple. So this is matching, right, with the previous H parameter, whatever we have found out, that is matching. So let's now take it to the other part, that is okay. So other portion is V1 equals to 0. So I will short the V1, right? So if I write the equations again, so if I make, sorry, not V1, sorry, not V1, that's why I always tend to forget, right? Not V1 equal to 0, I have to make I1 equal to 0. So I1 equal to 0 means just make this open circuit. So V2 is here only, so V1 is here only, and this is my V2, and I don't care about I2, I2 can be anything. Okay, so I1 is 0. So if I1 is 0 now, mainly I am interested in the H12, that is V1 over V2, and H22, that is I2 over V2. So what is my H12? So it is V1 over V2, right? So this voltage is V1 actually, this voltage is V1, and my I2 is 0. So basically, right, it is like a series divider, voltage divider. So this whole voltage is V1, right? Because this point voltage is plus V, this is minus V2. So this is plus V2 minus V2, right? This is the potential across these 2 points. So these two are in series because this is 0 current. So whatever current is coming from here, same current is going here, right? So these two are in series. Basically the whole V2 potential is across these 2 points, right? So it is like a voltage divider circuit. So basically V1 is the voltage across the 4 ohm. So what I can write is V1 will be the voltage division of V2 into 4 divided by 6 plus 4. So it will be V2 into 4 divided by 10. So it will be 0.4 V2. Okay, so this is my V1. This is my V1 value equals to. So what I have to find out? I have to find out the ratio of H12. H12 is V1 divided by V2. So it will be V1 divided by V2, that is 0.4. What about H22? H22 is I2 divided by V2. So it is very simple. It is the admittance seen from this. So I can find out the impedance and then just take the inverse. So impedance is 10 parallel with 10, right? So it is 10 parallel with 10, that is the impedance, and if the inverse of this will be the admittance, so it will be 0.2 ohm inverse. 0.2 ohm inverse. So if I just cross check with the previous values, so it was 2.4, 0.4, minus 0.4, 0.2. So it is 2.4, where did it go, 2.4, then it is uh, 0.4, then it is minus 0.4 here, minus 0.4 here, and 0.2. The last parameter what I remember is 0.2. Yeah, so it is exactly matching. So both way will work. Whichever method you want to find out, you will be able to find out. Okay, so few things to note here is that like if someone wants to know, right, h11 is equals to what, h11, like another few key points that I'll write here. Key points that my h11 is equals to h11 is equals to what, h11 is equals to v1 by i1. Okay, when my when my v2 is 0. So is it something similar? So I remember my y11 was equals to i1 by v1 when my v2 is equal to 0. Same condition, right? Condition is same. So basically I can write this h11 as inverse of y11. Okay, but please don't commit this mistake that you write this as z11, because you will say that z11 and y11 are different. No, this is not correct. This one is correct, this one is correct, but this is not correct. Why? Because the condition for z11 was what, my current i2 equal to 0. Okay, there was no voltage condition, but here there is a voltage condition, so that's why. Same for h12. So h12 is what, h12 is v1 upon v2 when my voltage v2 is equals to, sorry, when my voltage, when my current i1 is equals to 0. Okay, so what you can do is you can write this in terms of z12 and z22. So this, right, I can divide by i2 on both sides, numerator and denominator. So this will be v1 by i2, this will be v2 by i2. Okay, when my i1 is 0. So when my i1 is 0, when my i1 is 0, v1 by i2 is what, when my i1 is 0, v1 by i2 is the z12, v1 by i2 is the z12, and when my i2 is 0, what is v2 by i2, v2 by i2 is z22. But remember the conditions, condition is i2 is 0, right? Make sure this is not same as y22 upon y12. Okay, just keep that in mind. So yeah, again now, like these are good things to know, these are good things to know. Okay, someday if y parameter and z parameter is given and you have to find out the h parameter, you can directly use this method without doing anything, without doing any complex calculation. Directly use this method and find out the y and h parameters. Okay, now what is my h21? H21 equals to my i2 upon i1 when my v2 is 0. So whenever some v2 is 0, whenever voltage is 0, that means you have to use the admittance parameter. Whenever current is 0, you have to use the impedance parameter. So again, if I divide by, like I cannot divide by v2 on both sides because v2 is going to 0, so I will divide by v1 on both sides. So this will be i2 upon v1 divided by i1 upon v1, while my v2 is going to 0. So this will be y21 divided by y11. Of course, remember the condition that my v2 is going to 0. And same for, can I be able to write everything in a single page? Same for h22. Same for h22. h22 is i2 upon v2 for my v1 is equals to 0. So this will be equals to v2 upon i2. v2 upon i2 is there. So again v1, sorry, v1 is not 0, right? Sorry, i1 is 0. So again I have to use the impedance parameter. So it is basically what, it is the inverse of the z22. Of course, remember the condition where my i1 is equals to 0. This is the condition. Okay, this is the h22 basically. So yeah, this is how you solve the like questions if for some reason you have been given the y and z parameters. So if y and z parameters are given, you can use this like formula. So this, right, let me color this thing. Okay, so what I will do is I will give you like few things as homework. So this is a very good question which I want you to try it out by yourself, right? This is a very good question. I want you to try it out by yourself, okay? And yeah, in the next lecture we will solve this question, and in now we will start with the ABCD parameters, okay? So let us discuss about transmission parameters. So transmission parameters are also called as ABCD parameters. And why are they called transmission parameters? Because they are used to characterize transmission lines and microwave systems. So transmission lines in the like power systems, you will learn this in the power systems. Of course, I will teach you power systems, so you will learn this in the power systems. Also in your EMFT, right? For EC, I'm talking about EC. In EMFT, EC, in microwave systems, transmission line are used to characterize any network, any linear two-port network. Transmission parameters are used to characterize transmission lines. Okay, that's why the name transmission parameters. Now, what are transmission parameters? Here, transmission parameters are actually used to characterize my transmission lines where I express my input port variable in terms of output port variables. So what are my input port variables? That is V1 and I1. Okay, and what are my output port variables? That is V2 and I2. Okay, so how to remember this? How do you remember this? Very simple, right? Remember that I have to write my input port variables in terms of output port variables. What are my input port variables? V1, I1. So that's it, done. What are my output port variables? V2, I2. Very simple, right? Just write this much and you will be able to memorize. Inverse ABCD parameter will just be the opposite. So V2 will come here, I2 will come here, V1 will come here, I1 will come here. Okay. Now there is a huge confusion. So equation is not same like the previous one. So I have A V2 here, that is the constant, minus B I2, and I have C V2 minus D I2. So this negative sign is there. Previously we never written a negative sign. Why is there a negative sign? So if I tell you that like in your home, your mom keeps the bottle of milk or packet of milk on the second row of your whatever fridge, refrigerator, right, of your fridge. One day what happened is your mom kept it in the third row. You became very angry, right? You told your mom, you always used to keep the milk in the second row. Why have you kept in the third row? I was searching for it, I was not able to find it. So you were accustomed that your packet of milk should be in the second row. So when we write transmission lines, right, when we draw the transmission lines, we are accustomed that my direction of the current of the input port will be incoming here. Okay, so if I draw a simple transformer, okay, so we are accustomed to a simple transformer that the from the input side, from the source side, current will go from the source to load. So this will act as a load. So this is I1, this will act as a load, this thing will act as a load, and from the source I'm delivering the power. And again, on the right hand side I have a load connected here in the transmission line. Obviously there are transformers, there are multiple things, I'm not going into the details here, just explaining you the basic things, that there is a load. So we are accustomed that the current again I2 will be coming here. Now this will behave as a source, okay, to what? This will behave as a source to this load, okay. So we are accustomed on seeing the current on this right hand side direction. But the problem is, in two-port networks, we have learned that we write our currents going inwards to the network. All the currents are going inwards to the network. Everything is going inwards to the network. Nothing is coming out. Okay, so everything is going inwards. Then there is a problem. Right? So to mitigate the problem, what we do is, although our direction of the current, right, of any previous two-port network, if you have seen, the direction of the current, voltage is fine, voltage does not have any problems. So this is the voltage V1, this is the voltage V2, and the direction of the current is incoming. So this is fine, right? This does not have any problem. So this direction and this direction is fine. But here the current was going into the network. But actually we are accustomed to seeing current going out of the network. In transmission line, we are accustomed to seeing out of the going. We are accustomed to see the current going out of the network. So that's why, to fix that, because humans, right? We are humans, so we are very comfortable with which we have already seen before. So what we do is to make this, to change the direction. I want to change the direction. How do I change the direction? Just multiply a negative. Okay, so basically if I say that I have a wire here and minus 5 ampere current is flowing in this direction. So you can represent the same thing as I have a wire here and plus 5 current is flowing in the opposite direction. Negative just talks about the direction. Basically whatever direction you had initially assumed, you have to opposite. You have to make it opposite. So same thing I will do here. Because we are accustomed to seeing the current going from load source to load, that's why we will change. This is specifically for transmission parameters. This is specifically for transmission parameters. For everything else, it remains same. So I will change the direction. So what I will do is I will multiply a negative sign and change the direction. So multiplication of a negative sign actually helps us change the direction. Okay, so this is minus I2. So yeah, now I hope you have, like, I think this doubt is clear, right? So that's why, although this would have been plus I2, but here as the current itself is minus, so there is a minus sign here. So this minus sign is associated with the current. Minus sign is associated with the current. I hope now you have understood why there is a negative sign, why we write AV2 minus BI2 and not plus. Please keep this in mind. So here also, if you see here, the minus sign is with the current. Okay, so minus sign is with the current. Make sure to keep this in mind. So I will highlight this point. Minus sign is with the current. Okay, why it does not highlight actually? What happened? Okay, just oh that's cool actually. It just highlights this one. Okay, I did not knew. Okay, so yeah, keep this in mind. So I will just highlight this one. So there is a negative sign here. That is the reason. Okay, and these are known as T parameters, ABCD. So we will understand one by one what are ABCD. So again the same thing, right? I have written down the equation, so I will copy the equation again here. I will copy the equation. So I can directly say what will be my A. You can find out A by making I2 0. So A will be equals to V1 by V2, the voltage ratio or voltage gain, also sometimes we call it voltage ratio, when my I2 is 0. So it is open circuit voltage gain, something similar like that. Open circuit voltage gain, that is written over here as well. Open circuit voltage ratio, dimensionless. Okay, what about B? So B, open circuit because I2 current is 0, that's why open circuit. B right is minus of V1 by I2. Okay, when my V2 is 0, so it is short circuit transfer impedance. Short circuit, negative short circuit transfer impedance. So negative sign is there, so that's why negative short circuit transfer impedance unit will be ohms because it is impedance. What about C? C is again I1 by V2 when I2 is 0, so it is admittance. Basically it is the open circuit transfer admittance. So it is open circuit transfer admittance in Siemens. The last one is the current gain. Basically D is the negative of I1 over I2. Okay, so it is again when my V2 is 0, so it is short circuit current gain. Short circuit current gain. Okay, negative of short circuit current ratio or gain, whatever you want to call it. Okay, so another important fact that here my V1 and I1 are dependent variables and V2 and I2 are independent. So again, if anywhere my, like this, I think I have written previously here as well I have written, yeah, so here I have written right, that in ABCD parameters the variables V2 and I2 must be independent of each other. If they are dependent, right, then of course there will be a problem. If they are dependent, there will be a problem. Then ABCD parameter won't exist. So right here, else ABCD parameters won't exist. Same condition for the previous one, whatever we have learned, similar thing. ABCD parameters won't exist. Okay, so yeah, that was basically it about the short things. Now what okay, we have already discussed how to measure it. It's very simple, right? So if I copy this network, how do I measure it basically? So what you can do, right, for A and C, what we have to do, for A and C we have to make the current zero. So this will be open circuited, and we have to measure the voltage. We have to measure the voltage V2, V1 and I1 current. So here there will be a, basically there will be an ammeter, or I can use some other color. Here there will be ammeter, okay, and there will be a voltmeter here, and there will be a voltmeter here. Okay, let me just log this for a second. This will be V, ammeter, voltmeter. So this is the scenario, and of course my I1 is open circuited, so it will be here, right, current will be 0. Okay, and in the next case something similar we will do is, now the ammeter will be connected on the, sorry, not yeah, ammeter will be connected on the right hand side, and V2 will be 0. So V2 will be short circuited basically. So voltmeter will not be there basically, or voltmeter will not be there. So a ammeter will be connected here. Let me log this thing. So this ammeter will be somewhere here, and voltmeter will be here, and this will be shorted. And what else I have to measure? Okay, I have to measure the input current as well. So ammeter will be on the input side as well. So B and D, I have to measure the output current, input current, and the V1. So voltmeter will anyways be there, and ammeter also will be there actually. On this side also ammeter will be there. Okay, so this is how you measure the A and C, and this is how you measure the B and D. Okay, so these are the parameters basically. This is like same thing, right? So here few key points are written, like when does it exist or not, that I have already discussed. So it is very useful if I want to establish, a direct relationship between the input and the output uh, variables. Okay, electrical modeling of ABCD parameter does not exist because both equations in ABCD parameter representation express the input variables V1 I1 in terms of output variables. Hence there is no direct physical equivalent for this parameters, because both the input voltage and input current, right, both are dependent on the output voltage and output current. So we cannot actually model it electrically. So there is no electrical modeling, and that's fine, that's totally fine. Now what are the inverse transmission parameters? Just the opposite. Okay, I'm not explaining you much, just the opposite of ABCD parameters, that's it. Okay, so we don't need to go into depth here. Basically my V2 and I2 will be the dependent variables, dependent variables and V1 and I1 will be the independent variables. Okay, So that is just one thing. V1 and I1 should be independent. So basically we define our output port variable in terms of input port variables. Okay, that is what we do. And this, like here, right, we represent our parameters in small a, small b, small c, small d. Okay, again port current will be again negative. Here I1 will be negative. Okay, previously I2 was negative, here I1 will be negative. Okay, that is the only thing. Basically we are defining output in terms of input. So what is happening is, my, if I model the port, right, it will be somewhat like this. This is the network. So this time I am providing, let's say I am providing supply from the output. If I am providing supply from the output, then current is going from source to load. So current direction will be something like this, and then the load, let's say, is connected in the port 1. So here the current will be I1. But again the same thing, right? I have assumed, like, our assumption is current always goes into the port. So again it is opposite. So again a negative sign is associated with this I1. So that is the only thing that you need to keep in mind, except that everything else is same, right? V1, V2. So if you remember ABCD, capital ABCD parameters, it's very easy to remember the small ABCD parameters. Very small difference, minute difference is there. Okay. So yeah, this will be linear network. So now what are the conditions for reciprocity? So the condition for reciprocity for ABCD parameters is AD minus BC equals to 0. That is what? That is the determinant of the transmission matrix has to be, so not 0, sorry, has to be 1. So something similar was there, right? This was something similar was there in the H parameter, but in H parameter this was the condition for symmetricity. So if I go back here in the H parameter, the condition for symmetricity is determinant of H is equals to 1. So this, right, also can be written as determinant of H, determinant of G equals to 1, equals to 1. So same, like, so how do you remember? So you first remember the condition for symmetricity and reciprocity for impedance admittance parameter. For impedance admittance parameter, Z12 equals to Z21 for reciprocity, Y12 equals to Y21 for reciprocity, Y22 equals to Y11 for symmetricity, Z22 equals to Z11 for symmetricity. For hybrid parameters, H21 equals to minus of H12. It is somewhat similar to Z parameters, but just a minute difference is there, negative sign. Okay, so it is the condition for reciprocity. Same condition will be for the G parameter, minus, so G12 equals to minus G21. Okay, now symmetricity is quite different. Okay, so symmetricity is something new comes up. H parameter, determinant of H is equals to 1 for H parameter, determinant of G equals to 1 for G parameter. So this is the condition for symmetricity basically. Just hold on. Yeah. So this is the condition for symmetricity. Okay, now here things will get flipped. Things will get flipped here. Okay, so here again condition for symmetricity will be A will be equals to D. Okay, this is the condition for symmetricity. Same for the inverse T parameters. Condition for reciprocity will be the opposite of what? H parameter. So H parameter had determinant of H equal to symmetricity, determinant of H equal to 1 equal to symmetricity, right? So here I will have determinant of T equals to 1 as reciprocity. So yeah, this much you have to remember, unfortunately. So, and I think I have told you the sequence as well, how you can remember all of them in sequence, right? I've already explained you the sequence. So I don't feel like you will have much doubts how to remember it. Okay, so these are the few applications. So I will write here, right? So what are the symmetricity conditions? I think I have already written it. Okay, I don't, maybe I have summarized it, but here anyways I will summarize. So let me write few parameters. So here I have Z parameter, here I have Y parameter. Z and Y parameter are just same, right? Z and Y parameter are just भाई भाई, ये दोनों भाई भाई है, they are cousins. My H parameter, equals to G parameter. Then I have my ABCD parameter, and inverse ABCD parameter. Or small ABCD parameter. Okay, so this will be the condition for reciprocity. We will discuss the condition for reciprocity first. So the condition for reciprocity is Z12 equals to Z21 or Y12 equals to Y21. Here the condition for reciprocity, somewhere right we can, how do I write it? It should be somewhat like this. It could be somewhere like this. Here the condition for reciprocity is, if you remember, it was H12, it was almost similar as Z and Y, but negative sign was there. A negative sign was there. G12 equals to minus of G21. Here it will be completely different. That is the symmetry condition for each parameter. So it will be delta of capital T equals to 1. That is my AD minus BC equals to, so AD minus BC equals to 1. Okay. So and what about the AD minus BC equal to 1? Yeah. What about the condition for small t parameters? It is the determinant of t equals to 1, that is AD minus BC equals to 1. Okay, this is the condition for small t. And for symmetricity, what are the conditions? Symmetricity. So I can use a different color. For symmetricity, here my Z11 will be equals to Z22 or Y11 will be equals to Y22. Here my determinant of H must be equal to 1. Here my determinant of G equals to 1. Here just the opposite, right? It will follow this one. Previously it followed this H parameter. Now it will follow the Y parameter. So Y or Z parameter, that is my opposite side main diagonal elements must be equal. So main diagonal elements is A and D. They must be equal. And in this case, in the small ABCD, it is small a equal to small d. Okay, so yeah, these are the things. And why are ABCD parameters used or transmission parameters used? You can go through and read about this. Okay, so now we will find the ABCD parameters for a few networks like this one. Okay, and at the end I will tell you a shortcut as well. Okay, how to find ABCD parameters really quickly. So we have to find out the ABCD parameters here. Okay, so what we can do is we can write the values here. So let's solve this together. Okay, let's solve this together. So if I solve this together, there I think is another one as well. Okay, this is short, this should not be short circuited. Sorry, I don't think this should be short circuited. Okay, my bad. This should not be short circuited, this should be open circuited. Okay, this should not be short circuited actually, just for a single impedance element, right? Yeah, my bad. So what is the ABCD parameter of this? What is my, if I write a KVL here, if I write a KVL, so I have to define my input variables in terms of output variables. So I will not take the I1 current, I will take the I2 current. So I2 current is what? Going in this direction. So the drop will be what? In this direction. Plus minus I2 into Z1. So it will be minus of V1 minus I2 into Z1 then plus V2 equals to 0. So V1 equals to V2 minus I2 into Z1. So from here, right, I can directly say what is my A. So A from this equation is 1 and B from this equation is Z1. It is not minus of Z1, no, because my B was with negative sign already. My B was already with a negative sign. So B will be equals to, so just be careful that like our actual port current is in this direction, right? But we had to like change the sign. We have to write minus I2. So our port current will be same. Whatever we are solving, we will solve it same. Ultimately, answer I will give in opposite because it was minus I2 there. Why it was minus I2? I have already explained in the starting, right? ABCD parameters. So that's why this is not correct. This will be plus Z1 only. Okay, just be careful regarding this. So while solving the questions, so I will write here while solving the questions. Solving questions, you write current according to your port directions. You write currents according to what you know, right? What we know always, it is incoming to the port according to your port directions. Then at the end you add this negative sign, whatever negative sign is there, you add the negative sign. So at the end you think about negative sign. Okay, so yeah, that is the important point that what you have to keep in mind. So what is the like B is Z1, so what about the other one? So I have to write I2 in terms of the output ports. So what is my I2 equals to? So my I2, right, is very simple, right? I2 is sorry, I1 is minus of I2, that's it, right? Because like this current is going here, this current is coming on the left hand side, opposite direction. So I1 is minus of I2. It's very simple. So I1 is minus of I2. So that's why here negative sign is already attached. So there is no V1 here. Sorry, there is no V2. That means what? That means my C is 0. That means my C is 0 and my D is not minus 1, 1, because already in the equation I have a minus sign. Already in the equation I have a minus sign. Where did it go? Yeah, already in the equation I already have a minus sign. So whenever, if you get confused, right, always write down the equation. So if you ever get confused in the question, always write down the equation. So I will write down the equation. Okay, so that confusion is not there. So what about the part B? So what is the ABCD matrix here? ABCD matrix, T matrix is here, right? We have like our A is 1, B is Z1. So 1, Z1, 0, and this is 1. If I notice, what is the determinant of this matrix? Determinant of matrix is 1, which is absolutely correct because this is a like a passive network, and a passive network is always reciprocal. Is it symmetrical? It is symmetrical, right? Because if I divide this Z1 into two parts, so this Z1 can be divided like this, Z1 by 2, then here Z1 by 2. Okay, so of course it is symmetrical, right? On the left hand side and right hand side it is absolutely mirror image. So that's why it is symmetrical. That's why my A is equals to D. Okay, now let's check for the other network, that is this one. Let's check for this network, right? Let me cut this. So what I can say is my voltages, like again, if I want to write my currents and voltages, right? Let's say I want to write my voltage in terms of port current I2 and V2. Can I write it? So what will be this current basically? this is the voltage, right? So current across this will be V2 by 2, or I can directly write a KVL here. If I directly write a KVL, this will be minus of V1 plus V2 equal to 0. So V1 equals to V2. So here of course my A is 1 and my B is 0 because I don't have any I2 term here. What about the I1 current? So what is I1 current? Now I1 is not equals to minus I2. It is a bit different, right? So what is the current through here? Current through here will be the voltage across the impedance divided by its impedance. Voltage is V2 divided by its impedance is Z2. Okay. So I can write a KCL in this node, right? I can write a KCL in this node. If I write a KCL in this node, that is my minus I1 minus I1 minus I2 plus V2 by Z2 equal to 0. So I can directly write my I1 as V2 by Z2 minus I2. So from here I can directly say that my C will be equals to 1 by Z2, and unit is also fine, right? Because unit of C is in the ohm inverse, and I2 basically my D is 1, not minus 1, D is 1. So again the network is symmetrical, and again is the determinant 1. Yes, the determinant is again 1. So we can cross verify this. So this will be T network matrix. This is the for the B part, this is for the A part. Here my A is 1, B is 0, my C is 1 by Z2, and my D is 1. Okay, so what is the determinant of matrix? Determinant of the matrix is 1, hence it is reciprocal, and it is reciprocal, right? Because only passive components are present. And what is the symmetricity condition? So A is equals to D, again it is symmetrical. Is it really symmetrical? Yes. So if I break this impedance into two parts, so I will delete these things. If I break this impedance into two parts, one impedance is Z2 by 2, other impedance is also Z2 by 2. So this, right, Z2 by 2. So again it is mirror image, right? Again it is mirror image on the left hand side, on the right hand side. Okay, so again we have to prove that it is symmetrical. Now let's solve for a general case, and I will conclude like why are we solving these networks. I will put a conclusion here. Okay, so let me solve for the final one. Final one will not be that simple. So for the final one, uh, first let us write our V1 in terms of I2. So here, right, current I2 is incoming, okay, and here I1 is incoming. What is this current? What is this current? This current is V2 by Z2, right? This current is V2 by Z2. This current is V2 by Z2. So what will be this current, right? This current will be I2 minus V2 by Z2 if I apply a KCL at this node. So I don't want to write in terms of I1 because I have to write V1 in terms of the output parameters. So now if I apply a KVL in this loop, if I apply KVL in this loop, or you can apply a KVL in this loop as well, whatever is suitable, like it's the same thing only. So basically I can write my minus V1 plus I1 into Z1, not I1, sorry, because I don't want to write in terms of I1 current, right? I want to write in terms of I2. So this will be I2 minus V2 divided by Z2 plus V2. just completing the KVL. So from here my V1 will be equals to V2 1 minus 1 by Z2. Okay, so it is equals to 1 minus 1 by Z2 or 1 minus, this is plus. Okay, I made a mistake, right? Because current is coming like this, so the how will the drop be? Drop will be like this, right? So I have to write the negative sign here, so that was a mistake from my end. This will be negative. Okay, so if it is negative, this will be minus minus plus, so this will be plus 1 plus 1 by Z2. Okay, sorry, Z1 by Z2, Z1 by Z2, because Z1 is getting multiplied here. And what about I2? I2 is with a negative sign, that is minus Z1 I2. Okay, and what about the current? So current I1 in terms of voltage, if I want to write, so I1 current, I1 plus I2 equals to V2 by Z2. So I can write a KCL, I1 plus I2, KCL at this node, I1 plus I2 equals to V2 by Z2. So I can say my I1 current equals to V2 by Z2 minus I2. So from here I can directly write the ABCD matrix. So this is the matrix for the C network. Okay, so this is equals to V2 is 1 plus Z1 divided by Z2. Then I have Z1 here. Then I have 1 divided by Z2. Then I have 1. Okay, so this is basically a formula. If you want to remember, you can remember the formula, but I want to come to a conclusion, right? So like you can remember it, but I also tend to forget it, but it's really useful. It will come in handy in the next lecture, because not in the next lecture, in the next to next lecture, where we will study about cascading of networks. So like there is a pattern here. If you notice, there is a pattern. What is the pattern? Pattern basically is, if I would have written the, basically, right, these two networks are in cascade. This network, oh, sorry, this network and these network are in cascade. How are they in cascade? I will explain. So let me just copy the whole thing, copy the whole matrix. So let me take this current as I2 dash, and this current as I1 dash, and this current as I2 only, that is fine. And this voltage as V2 dash, this was V1 dash. Okay, and let me name this terminals as X, Y. Okay, and this is also XY. So if I connect these terminals, okay, I will get this network, right? I'll get this network. So this multiplied cascade with each other, this will give me this network. Okay, so in what happens if two networks are in cascade, that is the output port of one of the network is connected to the input port. So this is the output port for this network, and this is the input port for this network. So if the output port and input port are connected, don't worry, we will learn this topic in the next to next lecture, but I'm just giving you a preview. Connected together, then it is known as cascading of networks. So we will learn this, don't worry, we will learn this in the later parts. So like what is the conclusion? Conclusion is that if they are in cascade, right, so individually if I know the T parameter of network 1 TA, network A, and individually if I know the T parameter of network B, TB, so if I do the matrix multiplication, I will get the T parameter of network C. So that is the conclusion that I wanted to give you. So we can prove it as well. So what was the TA matrix? TA matrix was this, right? And what is the TB matrix? TB matrix is this. Okay, so TA into TB will be equals to this 1 Z1 0 1 into 1 0 1 by Z2 1. So this will be equals to 1 plus Z1 divided by Z2, and this is 0 into Z1, 0 into 1 by Z2 plus 1. Okay, so if we cross verify, this is actually equals to my TC that we derived, right? This is actually equals to TC that we just derived. 1 plus Z1 by Z2 in Z1 1 by Z2 1. So if you can remember this, good, but how do you remember it? How do you remember it? So how you can remember is for the T parameter for this network, right? How can you remember the T parameter or the ABCD parameter for this network? What you have to remember is, you have to remember two things. So first of all, what are the units of each elements in the matrix? So if I remember, this element, right, was B, and B had units of ohm. Sorry, B had units of ohm. Yes, B had units of ohm. Basically, V2, I2, right, are the independent variables. So it is V1 by I2. V1 by I2. So I have V1 by I2, so it has units of ohm. So I will choose the series element. Okay, I will choose the series element because in series unit is ohm. So here, that's why I will choose Z1. Now C has the unit of ohm inverse. So I will choose the shunt element. So whenever things are in parallel, I tend to go towards conductance. So I will choose the shunt element. So what is the conductance, or sorry, what is the admittance of this shunt element? It is 1 by Z2. It's done, right? Now it's done. Now I just have to think about this and this element. So one thing you have to remember is the last element is unitless. Last element is unitless. And I have to remember that D will be equals to 1. This you have to remember. The last element will be equals to 1. Now you can take help of the reciprocity condition. What is the reciprocity condition? Reciprocity condition is determinant of the ABCD matrix will be 1 because it only consists of Z1 impedance, like passive elements. So if even if I assume here A, so A into 1, that is A, plus minus Z1 divided by Z2 must be equals to 1. So from here, from this equation, I get the value of A. So A will be 1 plus Z1 divided by Z2. Okay. So remember this one, this one, this one. Ultimately, this one you will automatically find out with the condition determinant of A. So if you tend to forget, this is how you can remember it. Okay. So yeah, that's what basically, that's it basically for this network. So now I will give you a few homeworks. This is the first one, and this is the next one. I think this is the last one. You try it out by yourself, and in the next lecture we will solve all the assignment questions, and after that we will start with a new topic, that is interconnection of two-port networks. So I hope you have enjoyed this lecture. If you did enjoy the lecture, make sure to hit the like button and comment down below which portion you enjoyed the most. I will see you in the next lecture. Until then, happy learning.